guess first thing I had to announce is that those of you gung-ho who like to go grab the quiz right after class, it's not posted yet, so hold back a little bit on that one. It might be delayed a bit. Try to get it up as soon as I can. Just got a couple of appointments this afternoon, so we'll see. I mean, I got to make it hard. Right? I mean, it's challenging, I'm trying to figure out ways to give you all conniptions over the weekend. That's light to my day. All right, so we left off last time, embarked on a path toward calculating saturation overland flow. And to get there, kind of breezed through Darcy's law. I thought maybe I should back up a little bit, whether you're familiar with Darcy's law or not. I think we can all probably get something out of okay, let's back off just a bit to the basics. And it'll also help us with understanding the whole infiltration thing as well as the saturation overland flow. So it'll help with both sorts of. All right, let's just make this pretty simple. Let's say we've got a long tube and if you want, we can put in a radius. And I'm just going to orient an x direction along the flow path. So I'm putting in water at this end. I'm going to set up a couple of little tubes here. I'm going to call them piezometers because that's what we call the things that we use to measure what the head is below the water, below the ground surface. And so we might suppose then that we've got some head tank up here pushing water in there, and that therefore we'd have water rising to some level here and probably falling to a lower level here, at least if we have some porous medium in here. I mean, even if we don't, in general, if there's a finite roughness to the tube, we're going to lose head along the flow path. Okay, and head is just the sum of the pressure and the elevation. All right, so if, let's say then this distance here is delta x. I've got these heights rising to some elevations above some arbitrary datum. And I'll call this H1, this H2, H for head. And so Darcy's law says that the volumetric flow rate, that is the discharge per cross-sectional area, is proportional to the head gradient along that flow path. Okay, so that means, let's see, our volumetric flow rate has units of length per time. It's not a velocity, it's a flow rate per cross-sectional area. It just has units of velocity. Our volumetric flow rate is equal, well, that constant of proportionality is the hydraulic conductivity. And then, of course, we've got our head gradient, as I said. Okay, so we'll give this a little Q. K-sat. The head, let's see, let's just get the basics here. Head at 0.2, H2, minus the head at H1. Reminds me I'm going to need a negative sign. Sometimes sort of blow that off, but let's just be clear. So H2 minus H1 over delta X. If you want to know why I know that I need a negative sign, well, I know that water flows downhill, and so head gradient is going to be defined this way. I know water's flowing this way. The head at 2 is less than at 1. So I hope that's reasonably clear. As in the limit as delta X goes to 0, we have Q equal to minus K sat dH dx. All right. So probably you've seen that before, but just in case. What's in the saturated hydraulic conductivity? That's and I keep kind of being a bit anal about putting a sat on it, and I'll get to that in a bit. But what is that K-sat? Well, it combines permeability, which is, of course, a material property, has units of length squared. It has gravity, which of course is length per time squared. And that's a property of our planet. And it has kinematic viscosity, which has units of length squared per time. Property of the fluid. So we're combining properties of the material, the planet, and the fluid. So typically we use a little K for permeability, and nu, lowercase Greek letter nu for kinematic viscosity. Let's just make sure the units are working out right for me. L squareds cancel. One of the T's cancel length per time. Yes, so saturated hydraulic conductivity. Hydraulic conductivity should have units of length per time.
Does rho come into play at all in this?
It would if I used the dynamic viscosity, which is mu, which is, let's see, that would be I think that, if I'm remembering correctly.
Yeah. The symbol for kinematic viscosity.
Symbol for kinematic is nu, Greek letter nu. Symbol for dynamic is mu. Mu, whatever. Okay. Now, let's consider for a minute water draining vertically and freely above the water table, but essentially saturated just not below the water table. That is, the water is draining through under the force of gravity. So let's consider then if we just tilt our tube up vertically, So now we've got our water in up here. We can still orient our x direction parallel to the tube. And now we've got, again, the same delta x here. All right, if I've got no water table, so no pressure, the head is just the elevation. Right, if head is pressure plus elevation, then I don't have any pressure. It's atmospheric pressure, which we, by convention, assign a value of 0. Floor pressure is 0, then my head is just the elevation. What's the difference in elevation then between the top and the bottom? Delta x. So here my volumetric flow rate is head gradient in gravitationally draining water is 1. So I mentioned last time that our criterion for trying to figure out whether we might have infiltration excess overland flow, which is when precipitation exceeds the possible infiltration rate into the soil. I said, well, if the precipitation rate is greater than the saturated hydraulic conductivity, then we've got infiltration excess overland flow, and this is why. Because our maximum flow rate per cross-sectional area vertically is equal to Ksat. So for infiltration excess overland flow, we get that when the precipitation rate is greater than the saturated hydraulic conductivity. Now it can get a bit more complicated than that because I've been real careful about always putting a sat on this and talking about, well, maybe it's not technically saturated, but it's draining, it's 0 pore pressure, but the pores are all filled with water. Why am I so anal about that? Has anybody ever emptied a cooler below a juniper tree? So I go camping in the desert every summer, and at the end of it, we're dumping out our water and are emptying the melted ice out of our coolers, and we set up our kitchen under a big juniper tree. It's nice because not much grows under a juniper tree. Partly it's shaded, but partly plants can't drink water under a juniper tree. Because if you ever try that, if you ever pour your cooler out onto that litter and dirt beneath the juniper tree, you might notice that it beads up, doesn't soak in at all. You could probably get it too, but it's pretty remarkable how long it takes. Now that's a case where I have a surface that's hydrophobic. Most soils aren't hydrophobic, but most soils actually do tend to let water stick to them. And so if I don't have saturation, then I've got surface tension, what we call it, right? If you've ever built a sandcastle, and I hope all of you have, then you know that you use wet sand. You don't use dry sand because you can make a vertical wall with not saturated sand, but with moist sand, because that surface tension will hold the grains together. Now, it's a bit of a double-edged thing because, hydraulic conductivity does depend on that moisture content. And in order to think about that, let me draw, if I just draw two different tubes, a thin tube and a fat tube, which is the water going to drain more easily through? The fat tube, of course. Let's draw a couple of different pore situations. That is, pore spaces in a porous medium. Drawn them as similarly as I can because I want them to be similar, because I only want the difference to be how much water content there is. So if this one is not saturated, we're trying to shade in the wet part of it, and this one is saturated, in which case does the water have the bigger tube? Right? Here it's got the whole pore space to flow through. Here it's only got the thin, it pinches out. It's got to flow through those thin spots. Now, it's somewhat aided by the fact that the water is held in tension, that it's going to tend to pull the water in a bit. But in terms of our hydraulic conductivity, it's the maximum when it's saturated. Okay. Interesting facts. So, in basic summary, we're going to generally get infiltration excess overland flow when precipitation rate exceeds the saturated hydraulic conductivity. The details of, before the soil is, before that hydraulic conductivity reaches the saturated value, the details are actually pretty interesting. That means really complicated. So let's move along then. Just so you know, it can be more complicated than I've written down. Just don't want to lead you on to think that it's just always that simple. Okay, back to saturated overland flow then. Erase these. Let's draw up our convergent slope. So I've got a slope. It is convergent. All the rain falling on here, and there is rain falling on it. And it has a rate P. I've got a soil thickness here, I'll call capital H. I've got a contour width down here that I'll call W. And let's say, for argument's sake, that I've drawn this to represent the place where I start getting saturation overland flow, so that my water table is at the surface just right here. And so any water table I've got hits the surface right there, but in general goes to 0 at the divide up there. Okay, so there's my water table. I've got an area. And a slope angle. All right. discharge from rainfall. What did we say that was? Remember, we said it's not the beginning of November, it's the end of November, maybe December. It's been raining forever. And so the flow out equals the flow in. So the discharge down here from the rain is just that precipitation rate times the area of the slope. From Darcy's law, said, well, okay, the volumetric flow rate's proportional to the head gradient. What's the head gradient here? Well, I don't know exactly, but a good approximation is the topographic gradient. And it's a pretty good approximation. Especially if I've got, a relatively uniform soil thickness over a relatively impermeable bedrock layer down here. So my head gradient is, we'll just be precise about it, sine theta, sine of the slope angle. And the volumetric flow rate, okay, so saturated hydraulic conductivity, and then that was flow per cross-sectional area. The cross-sectional area is then just the total soil thickness times that contour width W. Okay, so Ksat times the soil thickness times the contour width times sine theta. So, if and I want to know something, this is, well, okay. Whatever I want to know, this gives me an equation to solve for it. Because I can say, well, these two things are equal, at least in the ideal kind of case that I've outlined here. And so if I set the one equal to the other, then got a nice simple equation. And then I can say, well, what do I want to know? What do I know and what do I want to know? Well, say I know everything except I don't know, I want to know what say we want to know the precipitation rate for saturation overland flow at that given spot. Well, that's pretty simple. All I got to do is divide both sides by the contributing area. And we've got P equals Ksat. Soil depth, contour width, sine theta, divided by the contributing area. The larger the contributing area, the smaller the precipitation rate necessary to fill a given cross-section. That makes sense. The smaller the saturated hydraulic conductivity, the less flow I can fit through, the less precipitation I'm going to need to saturate it, and so on. What else might I want to know? I think I mentioned last time, maybe I want to know the contributing area per contour width. Given given everything else, given a certain precipitation rate and so on. Again, real straightforward to solve. All I got to do is divide both sides by P and W, and I get A over W equals K sat times H times sine theta over P. Larger precipitation rate, smaller necessary contributing area per contour width. This has units of length, by the way, necessary to saturate. Okay, so that makes sense too. How about this? Suppose my angle of repose, I haven't mentioned what any of these numbers are. Suppose my angle theta is 25 degrees. Pretty steep. Not ridiculously fall off the hill kind of steep, but pretty steep. Is that raising any alarm bells for anybody if we're talking about saturating something that's 25 degrees? Let's say my angle of repose, just to maybe throw a hint at you, is 37 degrees. Anybody remember we set up, yeah.
21 degrees that was better.
Yeah, so we said if we've got zero cohesion or neglecting cohesion, and we said, well, okay, there's going to be some angle below which no amount of saturation will cause it to fail as a landslide. Conversely, there's an angle above which some level of saturation, if we have zero cohesion, will set off a landslide. And for zero cohesion and 37 degree angle of repose, you're right, that angle was 21 degrees. So an angle of 25 degrees for a slope angle, well, depending on the cohesion, we might not get saturation over land flow, we might get a landslide. So, maybe we want to say something about how close to full saturation we could get it. Let's revise this slope drawing over here. Let's say that instead of filling it all the way up, that instead I'm going to fill it part way up. And now instead of big H, I've got H sub W. Okay. I've basically got, I've got the same equation, except I've changed the subscript on here for what the cross-sectional area that I can possibly fit through is. In some sense, I've made it more general, right? I said, well, HW could be as large as the full soil thickness H, but it could also be smaller. And so, in that case, I'd have to rewrite that. Like so. Same equation, all I've done is put a subscript here because now I'm talking about, well, I may not have full saturation. So now let's say, maybe I know the precipitation rate and so on. Let me And HW was something that was in my factor of safety equation, I might recall. Maybe I ought to know that. So let's say, okay, we can solve for what HW is if we divide both sides by k sat W and sine theta. And then I can go to my factor of safety equation. Remember, the factor of safety is defined as this ratio between the magnitude of the shear strength and the shear stress. Shear strength was what? That's friction and cohesion. Shear stress is just that part of gravity that's tending to make stuff fall downhill. I had a relatively memorable form. Now, when we were coming up with our slope classes, we said even with zero cohesion, there's a class of slopes that will never fail, given a value of phi. And so in that case, we said, okay, let's set cohesion to 0. And with phi is 37 degrees, we came up with theta of 21 degrees. Okay. So now I can do this, right? I can say, okay, if I've got precipitation, contributing area, the rest of it, I can find out what my level of saturation is in the soil. I can plug that into here. And what's my criterion for when it's safe or unsafe? Greater than 1 or less than 1. If it's greater than 1, then what? Yeah. If it's less than 1, it's unsafe. If it's greater than 1, it might, I should say it might be safe. If it's less than 1, it's pretty definitely going to go. Greater than 1, I'd like it to be a lot greater than 1 personally, if my life depended on it. But that is the criterion. So.
What would a lot greater be, like 1.8 or like 72?
I'd personally like 10 or 100, really. I mean, I don't know. I haven't done that calculation, though. But, I've also never, lived in a place that was, done slope of something really steep and wet, either. Something to think about. Remember Oso? Big landslide, killed a bunch of people in Washington. They said, nobody could have seen it happen. Nobody could have foreseen this. That's crap. A colleague of mine did the numbers. He ran 2 scenarios. And the sort of default scenario, he came up with a factor of safety of 1.2. And then he said, well, let me be a little more conservative and run a little more dangerous sort of number. He came up with 0.9. And that supposedly is nobody could have seen it coming. I took a paper that another colleague of mine wrote about, okay, what the volume of landslide versus area inundated. I sketched it out. Yeah, last attempt. I mean, now, did anybody see it coming? Well, actually, yeah. My guy Dan saw it coming. And he told them, don't build there. And the county said, fuck you. I mean, anyway. So if I get a little exercise about this factor of safety stuff, it's because it really does actually matter. We can actually learn some valuable stuff. Okay, so if we wanted to be real sure of stability in this case, then we'd just set cohesion equal to 0 and set that equal to 1 and run away with it that way. Okay. You know, on the other hand, if we were trying to figure out a given failure, or we wanted to know like what's the necessary cohesion, we could do that too. Right? I mean, all we got to do is, you know, to sort of solve for that verge of stability is set this equal to 1 and do the algebra. You know, what is it that we don't know, or what is it that we'd really like to know that we don't know all that well? And one of those things is usually pore pressure. This is at least a way to get a rough number. It's not going to be an awesome, awesome number. It's not going to tell us everything, but it's going to tell us something. Certainly, if we plug in this in a number that we get from this into that, and it says that it's unstable, we ought to be scared. Because usually the pore pressure isn't really, this is going to do kind of a little bit of a half-baked job of things. Because this is, what did I say? I said it's raining forever, right? This is not going to do a good job if we're talking about what's the pore pressure induced by a pressure wave from a spike in rainfall intensity after it's been raining for a long time. And my soil column is unsaturated technically, but really wet. Pore pressure is 0 through the column. Exactly the sort of scenario that I was sketching up for our, you know, example of Darcy's law in the vertically draining case. That pressure wave from that spike in rainfall will transmit faster than the water will move. So, yeah, that's why this can tell us stuff about where the exact when we need to be a bit more careful. All right. Let's ask a different sort of question then. Because this is supposed to be about water in the landscape, yes. Tying it back to slope stability, yes. Channel networks, channel head. Where's the channel head? You know, I drew up a scenario in which we might have overland flow. What did I say, especially out in the field, about where the channel head would be? I said, well, if we've got, let's see if I can pull this off, pretty exaggerated, convergent but convex. And let's say right here is our beginning of our ravine, our notch. And then we've got our ravine continuing on down from there, and I'm not going to try to draw that on there other than an arrow. So I'm pushing it, just doing that much. Now what did I say? I said that we're going to have, that notch is going to stay there if the gophers can't fill it in. Well, what's the hill slope flux? Ooh. I'm feeling lazy, so let me think. How can I make this easy for me? You know what? I seem to remember there might be a shortcut if I make that mobile regolith a finite thickness. And if moreover I assume that it's constant in space and time, that makes my life a whole lot simpler. Because now I've got a weathering rate, and I can simply assume that the slope is set up for the gophers to do their work. They're going to move whatever is produced by weathering. But I have a weathering rate that's introducing material into that regolith layer, that mobile regolith layer. And again, if I've got some area now, anybody want to tell me what my flux is here? I mean, again, I'm trying to be lazy here. Not, I'm sort of being careless about, oh, well, am I talking slope normal or slope, or vertical, whatever. We're not going to get more accurate than ballpark anyway, so let's just go with something simple. Well, if I assume that my gophers are competent to move and keep that soil, that slope in shape, so to speak, then my flux at this point, due to my hill slope diffusive processes, and this is going to be a mass flux, is just going to be that density of bedrock times the weathering rate times the area of the hill slope. That's easy. I mean, presumes that I know this, but, there are ways to ballpark that if I don't know it exactly. Now, how do we figure out what the water can move? Well, let's just say that is more difficult. And let's make a stab at it. We'll back off, after today. Okay. But let's make a stab at it and see if there's a there to this sort of reasoning. So, how much stuff can the water move? It's tricky. I mean, what's the precipitation rate? It's all of the precipitation rates, kind of. At least all the ones that produce overland flow. How much stuff can we move with flowing water? Is it a function of shear stress? Or is it a function of stream power? Let's go with that one. That's pretty simple. We can say the rate of potential energy conversion to kinetic energy. I could go through the whole derivation, but I don't want to belabor that point. We've got some mass of water moving at some rate down a hill. That, I'll call this big capital omega, energy per time, energy per time per length. Is just density of water times gravity times my flow rate of water and negative of the slope gradient. I'll go ahead and simplify things for notation. Call that a capital S. Commonly, what we use for things like stream gradient, defined as positive downhill, so I can be a little lazier here with my minus signs and so on. Now, that's great. Let's just say then, or suppose perhaps, that my fluvial mass flux is just proportional to that stream power. And what's little k? It's just a k. It's just some constant. In which case, my fluvial mass flux might go something like that. But you know, I'm not real confident about this. Yeah, Gene.
I was going to ask what sediment size.
Yeah, see, it's all going to matter. So you know what? I'm going to go ahead and generalize that a bit. Because again, I don't know if it should be shear stress or stream power or even like raised to some exponent. So what I'm going to say is I'm going to just make it a bit more general. Say that my fluvial mass flux is proportional to discharge to some power, slope to some power. And that means that if I set the one equal to the other, I can actually solve for something, right? Now, moreover, I could go ahead and also make the approximation that Q is, say, precipitation rate times drainage area. Yeah? Yeah, just to make it so it's different from that one that I just put there. So if I use the same assumption for discharge that I did over there, and now I could set the one equal to the other. I don't know. Before I even do the algebra, I kind of want to, and I'm also running out of time, so I am out of time. Let's see if there's any there, because like I said, I'm pretty much out of time anyway. But what I would expect then is there to be some relationship between slope and contributing area at the channel head, and maybe in channels in general. These are data from the Oregon Coast Range, the Marin Hills, and the San Gabriel Mountains. The triangles are small channels, the filled circles are channel heads, the open circles are unchanneled valleys. And we've got slope, it's a little weird, slope on this axis, drainage area on this axis. And what we see is that, yeah, for all these different channel heads, if I've got a smaller area, or let's see, a smaller slope, then I need a bigger area. If I've got a bigger slope, then I need a smaller contributing area for a channel head. So it would appear then that there is some some relationship in terms of where the channel head is located, maybe even where channels are in general in this sort of space. But you know what? Before we plow into like, well, let's see what's what, we really need to back off into some fluvial mechanics, because I've just sort of wildly thrown up some, well, let's suppose it goes like this, right? Let's back off and work on our fluvial mechanics a little bit, and that's what we'll dive into next time.